It's thought that the ocean changed at this time to what's known as a Strangelove Ocean. This is named after the movie Dr. Strangelove from the 60s. Now, usually, the delta 13 C value of surface water is about +2 or so today. And that's because carbon-12 is preferred by plants, so they remove the carbon-12, leading to a proportional increase in carbon-13. So we can look at a change in the isotope values through time. We see a dramatic change at the surface, a dramatic shift in the carbon isotope value that suggests the ocean was killed. In the bottom water, it takes a long time for things to happen, so you don't get that same punch. This was a study done by Jim Zakos, Mike Arthur, and Walter Dean. Zakos was my quarterback in intramural football at Michigan. He's slow, so we made him quarterback, and it turns out he can't throw very well, so that was a mistake. Comets are icy balls of water, ammonia, methane, carbon dioxide, with bits and pieces of rocks and metal. Kind of dirty snowballs is the description that we used when I was a kid. The Oort Cloud is a spherical reservoir of comets that extends more than 1 light year from the sun. Now, when things pass by our solar system, they can disturb these dirty snowballs from this Oort cloud, and the result is they could go in any direction, depending on how close the disturbing body is. Some of those may come in our direction and hit the Earth. Asteroids, on the other hand, are composed predominantly of minerals and metals. They orbit the sun in a region known as the Asteroid Belt between Mars and Jupiter. If the big ones hit the Earth, that would be that. That would be the end of life as we know it. Maybe the end of life entirely. Now, siderophile or iron-loving elements like iridium can be concentrated in the interiors of metallic rocky planets and asteroids. So this is one of the reasons we suspect that the iridium anomaly at the KPG boundary is related to one of these asteroids from the asteroid belt. It's been suggested that there's periodicity of impacts and extinctions. This is a figure from your book from a number of years back. And a couple things jump out right away. First of all, the extinction events don't appear to correlate to the regular time pulses that are listed here. They're either before or after. Two, some are large, some are small, and statistically, there are other problems as well. So it's unlikely there's periodic impacts and unlikely that these impacts cause extinctions periodically. Other causes of mass extinctions. We'll take a look at a mass extinction that took place between the Eocene and Oligocene epochs of the Paleogene. So this is around 33.5 million years ago. 95% of the benthic fauna in the Gulf of Mexico went extinct, and no one knew why. The plankton record, the isotope record of plankton, showed no change before or after the extinction event. The plankton, unfortunately, only record surface water temperatures in the summer when the plankton bloom. So we wanted to take a new technique that was just developed and apply that to this extinction problem. Now, this new technique uses the ear bones from fish, structures called otoliths, which actually means ear stone. They're made of calcium carbonate, the same kind of calcium carbonate that a snail makes its shell from. So fortunately for us, all otoliths are not alike. They have features that allow us to differentiate between species. If you know what you're doing, you can pick up an otolith and say, this is a cod otolith. This is a butterfly fish otolith. This is a freshwater drum otolith, so on. And there are people like that. I know them. So first thing we needed to do was develop a temperature fractionation relationship between the isotope value of an otolith, of the otolith carbonate, and the temperature at which the fish lived. This is a combination of the isotope value of the calcium carbonate and the isotope value of the water, So there are three unknowns here: the isotope value of the otolith, the isotope value of the water, and the temperature of the water. If you know two of those unknowns, you can solve for the third. So we know the carbonate isotope value. Now we need to figure out either the water isotope value or the water temperature. So we developed this equation, raising fish under controlled conditions. When I was a graduate student, we had guppy, minnow, salmon, trout, and these are wild fish that were taken from deep lakes around the world. So we know that these fish, because they don't have swim bladders, stay on the bottom of the deep lake their entire life. The temperature does not change at the bottom of deep lakes, ever. You can get a feel for the age of this slide. This is when computers used to look like this 20 years ago. And what we're doing is basically training a robot to take tiny slices of material from these tiny objects, which represent a tiny slice of time in the past. This is what an otolith looks like inside a fish's head. This is a sagittae otolith, an asteriscus, and lapella. Three different types of otoliths. They occur in pairs. So there are 6 otoliths in most fishes' heads, bony fishes anyway. They're part of the hearing and balance and inertial structure in the fish's head. They tell a fish where it's going, whether it's upside down or not, and if something's approaching it, they can detect it using these features. Now, just for a little more clarity here, this is how we digitize things. We tell the computer that this is a growth band by touching the growth band with the tip of a tiny drill bit. So the computer then fits a curve through here. We have a nice smooth curve that represents a growth band. We do that again here, and then we tell the computer how many samples we want to remove from between these two digitized bands. And that represents our slice of time. Here is an image from a 3,300-year-old otolith recovered from a rock shelter in Tennessee. And we've digitized the growth banding in the otolith, produced those smooth curves, and then we're going to tell the computer to take 60 samples from here to here. If this represents 1 year, this would be that year divided by 60. So roughly 6 days per sample. Now these fish don't grow year round, so the resolution is a little better than that. And we could get down, in the case of clams, to a resolution of probably 4 to 12 hours in the animal's life. So what's the key here? The key is we're not drilling little holes. We're taking tiny slices using the edge of the drill bit. Each tiny slice is going to represent a couple days of time in the past. This is what the early version of this robot looked like. We now have a couple newer models here in Saskatchewan that are a little cleaner looking. We don't need these giant CRT units anymore. And here we have a control panel. My grad student threw these colors together. Kind of disturbing. So we can see the otolith looking down onto it here graphically, or from the side here. We can change the depth, change the path length, and by changing the mineral, we can determine the average sample mass, the specific sample mass, and we're shooting for enough material to get a good analysis. So we're going to take a look at some fish that lived 50 million years ago. These are modern conger eels. These are the fish you would see swimming through the Titanic when Bob Ballard sends a robot down, an ROV, to take a look at the bottom of the sea. You often see these things cruising by. They have stiff tails. They use to burrow tail first into the sediment. So fortunately for us, they spend the first year of their life at the surface. Then they go down in the deep water, burrow in with their tail, and they stay there the rest of their life. So the key here is we get summer temperatures when the fish is young, and we get summer and winter temperatures when the fish is an adult. So we're looking at these two species. These are artist renditions, obviously, of 34 and 33 million year old fish, roughly. What do we see? In the late Eocene, we can see a temperature range of about 6.7 degrees here. temperature range of 5 degrees here, so roughly 5 to 7 degrees temperature range. Summer temperatures are around 21, 22 degrees. Winter temperatures are around 15, 14, 13 or so, at the most extreme down here maybe. Okay, so we have summer temperatures around 21, 22, winter temperatures around 14, 15. In the Oligocene, we have summer temperatures of around 21, 22 again, maybe up to 23, 24, but winter temperatures are much lower. We're down to around 11, 12, 11, 11, 11 or so, and the temperature range is much greater. 9, 12, 10, 9, 9.5. So the temperature range is greater here. The winter temperatures are lower. The summer temperatures are about the same. This is why no one caught it before. The summer temperatures are the same in the Eocene and the Oligocene. It's the winter temperatures that are dropping. And winter temperatures are a killer. If you live here, you would agree. Also, seasonality is a killer. If you live here, you would agree. And I mean in Saskatoon, not in the Gulf. So maximum temperatures are plotted here. Again, all around 21, 22-ish for the most part. Minimum temperatures go from around 14, 15 degrees to 11, 12, 13-ish or so, warming up towards the end of the Oligocene. The seasonal temperature range is low during the Eocene, higher during the Oligocene. This is enough to kill these benthic organisms. If you have tropical fish at home, you know that you can't let the temperature vary wildly. You have a thermometer, you have a heater that is self-controlled. If the power goes out, your fish are done. More causes of mass extinction. This is Diot Anwotogalagat. This means, hi, how's it going in Irish? This is an Irish elk, a very large deer. This is compared to an ancient human here. And you can see that the antlers are substantial, around 10, 12 feet wide. I've seen the giant Irish elk in the museum in Trinity in Dublin. When you first walk in, this thing is, its antlers are as long as a pickup truck. So climate at the dawn of history, at the time of early civilization, we'll say 15,000 years ago. This is 13,000 years before Common Era. This is how we talk about time now. Common Era being equivalent to AD, BCE equivalent to BC. So 15,000 years ago, glaciers are shrinking, retreating, millions of tons of fresh water dumping in the ocean, sea level is rising. Our charismatic megafauna, like the woolly mammoth, Irish elk, giant ground sloth, all become extinct within a few thousand years. This is the woolly rhinoceros here and smilodon or saber-toothed tiger here. This is a giant ground sloth here. Other large animals include these giant beaver. Here is an artist's reconstruction of a giant beaver next to a black bear for scale. So these are black bear-sized beavers. This is a giant short-faced bear, also known as a cave bear. And for comparison, we have the giant short-faced bear here, an adult grizzly, and adult black bear here. So about the size, well, a little bigger than the largest bears that we see anywhere in the world today, which would be the brown bears in Kodiak Island and polar bears. We have mastodons feeding on trees that grew in these forests, and they ate trees like spruce and fir. We know this because we find them sometimes frozen, and particularly woolly mammoths with food still in their stomachs and intestines. As glaciers recede, the climate warms at the higher latitudes and becomes drier. So these cold, wet forests are replaced by broadleaf trees like oak, chestnut, and hickory that do much better in warmer, drier conditions. These changes contributed to the extinction of the mastodons, almost certainly, but hunting by Paleo-Indians probably almost certainly contributed to their extinction. So this reminds me of a story. And when I was a graduate student, we had been reading reports pretty regularly of people, mostly farmers, working in fields and finding animal trackways, mastodon trackways, or woolly mammoth trackways, everywhere. And it seems like every time someone excavated a bog, they would hit the remains of a woolly mammoth. So there was a dead elephant in every pond in the state of Michigan. People wondered why. So every Friday we would have a seminar, a joint geology-biology seminar, and have about 300 people or so. And then we'd all go to the pub together. Not all of us, maybe about 80 of us would go together. And one Friday afternoon, I went down to the pub, and a couple of people came up to me and asked if Dan Fisher had found me. And he was a professor at the university at the time. And I said, no, why would he be looking for me? He wants to talk to you right away. And I thought, what did I do? Did I say something in seminar that irritated him? What's going on? Dan never comes to the bar, so what's that about? They said, he's coming down here right now. Geez, what did I say? And Dan sits down next to me, and he says, hi, I was told to talk to you about this. I'm wondering what the best technique would be to recover gas from decaying meat. I said, where is this meat? He said, it's subaqueous. I said, so you have meat underwater? He said, correct. I said, how big is this chunk of meat? And he held his arms out, and it was about half the size of a file cabinet. And I said, what are you up to? And he says, I have this horse that we butchered on Jerry Smith's farm. Jerry was one of my PhD advisors. And we butchered the horse, and we put it in his pond, and we'd like to recover the meat and sample the gases that are being given off by this decaying meat. And I said, well, I guess I'd put a garbage bag in the water and move the meat into the garbage bag and then tie it off, kind of hug it, and then stick a syringe in it and pull the gas out, put it in a vacutainer, and then you could pop it on a quadrupole and determine what kind of gas is present. He says, oh, that's great. Will that work? I said, I don't know. No one's ever asked me this before. He said, what are you doing tomorrow at 8 a.m.? Oh, man. So Friday was the day that the professors would buy drinks for the graduate students. So very, very critical social period for us, given our extreme poverty as a graduate student. Okay, I'll be there. So 8 a.m., I was out on Jerry's farm. A friend of mine drove out in his wife's brand new car. Jerry had 4 pet wolves, or wolf hybrids. And as soon as we opened the car doors, the wolves ran through the car right across the front seat, all muddy, stinky. And he said, Natalie's going to be so impressed with that. And the car was a mess. So we recovered this meat from the pond. It really stunk. Really, really stunk. It had been there for 2 months at this time. And it was kind of whitish on the outside, like vanilla ice cream, and really soft. You could stick your fingers through it. So when we pulled it out, the wolves obviously know something's going on. They start howling. All the animals for miles in every direction on all the farms go off. The cows, the horses, everybody's upset. And then they took some of this meat. Dan built a fire, and he makes his own stone tools, as you do. And so he slices off some meat, cooks it up. Everybody puts some in their mouth. So I put some in my mouth. Now this is horse meat. The horse has been in the pond for 2 months, and it tasted pretty much like that. So I chew it up, thinking this tastes kind of like rotten horse meat, and I swallow it, and then I see everyone else spit it out. Why did that happen? So I ask, and they said, oh, we gave some to the wolves last month. It gave them horrible diarrhea. I thought, well, that's not cool. If it gives a wolf diarrhea, now it's been rotting for another month. What's it going to do to a graduate student? So I'm sitting there by the fire talking to these guys, and the big male, the alpha male, comes over and lays right on top of me. And this is after he had rolled all over the rotten meat. He's nice and shiny with rotten, stinky horse meat. And now he's on my legs. And I said, And they said, oh, don't worry, that means he likes you. I said, that's okay, but I wanted to go to the store on my way home to get some food, but now I have to burn my pants. Oh, it's not that bad. Oh, it's pretty bad. So what the heck was going on? This is a line from Oh Brother, Where Art Thou? I slaughtered this horse last Tuesday. I think it's starting to turn. This is Dan's subaqueous meat caching experiment. So Dan wanted to know why these elephants were in all these ponds, and they appeared to be butchered. There were scratches on the bones that indicated something happened to these bones after the death of the animal that wasn't caused by an animal chewing on them. Somebody was scratching at the muscles to get them off of these bones. So here we see Dan and Jerry putting the remains of the horse into the pond. This was one of Jerry's draft horses. It was a 2,000-pound Suffolk mare that died during foaling. So they cut the horse up using stone tools, put it in the pond on Valentine's Day. And I was there on April 14th, so exactly 2 months later. So after a month, it looked like this. After a couple more months, it looked worse. So I was there in between these two images. And the interesting thing that we learned, one of the interesting things, was the gas that was given off by this meat decaying was CO2, and the bacteria that were generating that gas living on this meat are the same as those that make yogurt. So essentially, this horse meat is being turned into really stinky horse yogurt. And that's good news for ancient people, and for me. It didn't make them sick, and it didn't make me sick because I was eating yogurt, a living culture of yogurt. And I was very relieved that it didn't ruin my whole weekend or life by eating that stuff. And other things were learned at the time, including the Paleo-Indians would place flat stones on a pond on ice, and the sun would heat those stones, and within 3 days the stone would go right through the ice. So no chopping, no augering was required. They would go out onto a pond in the wintertime, put a flat stone near the choice of meat they were interested in. It would work its way through the ice. They would pull the meat up. It was attached to a rope and a post. We find those in these deposits. And suddenly all this made sense. Finding flat stones around elephant remains in ponds in Michigan next to post holes and attached to ropes. The other thing that they did, which was kind of cool, is they took the intestines and they filled them with gravel and sand, and they used them as anchors, as weight. So they'd wrap this gravel-filled intestine around a chunk of meat and throw it in a pond, and that gravel-filled intestine would hold the meat down until they were ready to harvest it. Cool stuff for people living 12,000 years ago. They had it all figured out.